Sure, it's 3:30. We might as well get started on time. Hi, everybody. Welcome to Talk Math with Your Friends. We are super excited to see you guys here. We are still scheduling the rest of our fall lineups. I know there are only a couple more talks on our calendar, but stay tuned for those. Just to let you know that this talk will be recorded and uploaded to YouTube. So I want you to know you might be part of that recording. So Josh, before I introduce him and get us started, I just want to let you know about one of the things that we try and do in Talk Math with Your Friends is have people who we call our featured friends. And so these are people that will remain unmuted, you know, and be part of our studio audience, if you will. So if anyone's willing to volunteer to be that person, you just have to stay with your mic on and your screen on and answer any questions and be the smiling face. Anyone want to volunteer to be one of our featured friends for today?
I'm happy to if you need more.
Sure, Andrew. Well, you're hired. Anyone else?
I can probably do it.
Thanks, Lauren. You guys are awesome. Thank you for volunteering for that, and I'll probably stay on too. Okay, well, so I'll introduce our speaker. So today's speaker is Professor Josh Cooper. Josh Cooper is a professor of mathematics at the University of South Carolina, and his work's mostly in graph theory. He finished under Ron Graham at UCSD a while back, and he's going to be talking to us about the mathematics of Sudoku and some of the math that arises out of one of our favorite puzzles around here, right? So Josh, we'll hand it over to you.
Thanks very much, Kate, and everybody for making this happen. So I just share. Can you see that?
Yeah.
Yep, that looks good. While Josh is talking, I'll just say we'll have the chat going on, and BK is going to be our chat moderator. So if you have any questions for Josh and don't want to unmute, feel free to ask them there. We'll keep some discussion going on in the background too.
All right, thanks. So yeah, this is a kind of pastiche of talks that I've given at various points and update each time. You'll see like the materials at all different levels. I apologize if it's I'm saying something that's ridiculously simple, but anyway, jump in if anything's unclear, please, and hopefully you get something out of it. So yeah, just so we're all on the same page, right? What is Sudoku? Presumably, if you join the talk today, you know what it is, but right, so you have this matrix. It's filled with the 9 by 9 matrix filled with numbers 1 through 9, and then you can see lots of empty spots, right? And then the idea is that each number is occurs once in each row and each column, and also in these 3 by 3 blocks. But you're only shown some of the numbers, right? And so you have to figure out what the rest are. And trying not to, there's chat. Should I watch? I shouldn't be watching the chat. Okay.
Don't worry about
it. For example, that's a 7 there, I claim, because, well, you notice you can't see my mouse, can you?
You can
Yes,
just
we can.
see it.
You can,
Quite
okay,
faint,
good.
It's a little small, but it's visible.
Good. All right. So like in this spot and these 3, you don't get 7s, right? Because there's a 7 there, so there can't be 7s here. There's only supposed to be 1 in this row, and then there can't be a 7 there because there's already a 7 there, right? And so the only blank spot in this 3 by 3 box that's left is that little 7 in the lower right-hand corner. So got to have a 7 there. And then similarly, there's got to be a 1 there because can't be 1 there, can't be 1 there, 1, 1, right? So that's the only spot that you could put it, and you just keep going and filling in the spots until you've got everything filled in. Try doing that in Beamer. PowerPoint. Right,
Wait. Josh, is this really in Beamer?
No. That's what I'm saying is you got to use PowerPoint for these.
I thought that was going to be super rad. We could do this with Pixie. Come on.
Yeah.
Is that a threat? Right.
From Andrew, it might be.
Right, so suppose you're hired to design Sudoku puzzles, right? So you have sort of 2 jobs. As it turns out, it's not generally a good idea to just start writing clues down. You can get yourself stuck very easily. So probably the best strategy, and apparently this is what people actually do, is you write down a board. That's the finished, the solution, and then you erase some of the cells, right? And that's what you actually show people. And the cells that are left, that are given to the audience for the rest of the solving process, those are called givens or clues sometimes. So actually, just so that we're all on the same page with the terminology, here's a puzzle on the left, sorry, a board on the left, a completed board, and a puzzle on the right. And one of these entries you might call a cell. That's a row, that's a, just like matrix, row and column. That's known as a box or a block. That's a stack, a band. Like I said, those are givens or clues. And okay, so what makes a good puzzle? Well, first of all, you've got a really lousy puzzle if it's not what I'll call fair, right? So a fair puzzle is a puzzle where you can solve it, right? There is actually a board that completes the set of givens that you're given. And then also there's only one, right? It sort of wouldn't be very fair if there was some ambiguity in the solution. So, okay, when Sudoku was invented, apparently popped up around 1992, basically right away the question came up, what's the fewest number of givens that you can have in a puzzle, in a fair puzzle? The intuition is, right, too few givens and now you've got this ambiguity. And so you might try to answer this question by, let's say, enumerating all the possible sets of givens and then checking each one to see if it's solvable. And then once you've got the solvable one, see if they're unique, right? And then among those, you just output the smallest number of givens that you see. Seems reasonable. It's not, right? So if you tried this brute force strategy, it's eminently impractical. For example, if you think about, what cells am I even going to fill in with something that is not leave empty? Well, there's 81 cells, so 2 to the 81. That's about 10 to the 24 possible sets of cells that you have to fill with something. And actually, the situation is much worse, right? Because you've got 10 options for each location in the matrix. You can put the numbers 1 through 9, or you can put empty, and that means 10 to the 81 possible ways to fill in your proposal for a puzzle. It's actually really close to the current estimates for the number of atoms in the observable universe. People tend to say it's like 10 to the 80. So yeah, that's not possible. We're going to need to check each one of these 10 to the 81 things to see if it's a fair puzzle. Not going to happen. Right? So, all right, let's try to be smarter about it, right? So let's, you could, for example, start with, instead of trying to enumerate all the sets of givens, you could start with all the 81 given sets. And if you find a fair puzzle, then check the 80 given sets. And if you, right, like, you keep going until you get stuck. Well, this sounds sort of reasonable, but still you're going to get this combinatorial explosion. It's sort of very out of hand. And okay, one thing you could do is to start much lower than 81, because the thing is, we know that it's not 81. There are fair puzzles with many fewer than 81 means everything, right? So there are fair puzzles with many, many fewer than 81 cells filled in. Actually, there are puzzles known with only 17 of the 81 filled in. Here's an example of one I found somewhere. And by the way, like, you might wonder, is there only one of these 17 clue puzzles? And it turns out Gordon Royal has compiled about 50,000 inequivalent ones. I'll get to in a moment what I mean by inequivalent. Yeah, so there's a lot of them actually, with 17 clues. Interestingly, if you sort of look in the wild at puzzles, in the New York Times or whatever, they tend to be in the low 20s. These 17 clue puzzles, that's so constraining that the puzzles end up not being very interesting usually. So the really interesting ones tend to be in like low 20s. So yeah, so what do I mean by equivalent? Let me just start by talking about boards being equivalent. There's an equivalence relation. Namely, if here's a board, and you can think of it, instead of the numbers 1 through 9, I've got some 9 colors. So you can think of it as a coloring as much as a matrix. And okay, so 2 boards are equivalent if you can turn one into the other by some sequence of operations of the following form. So you can permute the rows and columns within each band or stack respectively, right? That doesn't change the property of being Sudoku. Its Sudoku-ness doesn't change. If you just sort of move cells willy-nilly, then you certainly can destroy its adherence to the rules of Sudoku. So you got to be a little careful, but permuting the rows and columns within a band or stack is safe. And of course, this gives you 3 factorial, because that's permuting within each column or each band, for example. And then there's 6 options here for where you're going to apply that operation. So that's something like 6 of the 6 operations that generates. And then notice you can also permute the bands themselves, right? So 1, 2, and 3 here could be swapped around. A, B, and C can be swapped around. These are all operations that preserve the property of being Sudoku board. You can also permute the colors, right? So permuted some colors. That, of course, also preserves Sudoku-ness. And it turns out that that's it. So those are all the operations. The group that those generate, which, as it turns out, has 3,359,232 elements, that's the Sudoku group, and that's the thing that acts on this board. And that's the only set of operations which are guaranteed to preserve the rules. And you might wonder, wait, couldn't I turn the board 90 degrees? Or couldn't I transpose it? And the answer is yes, of course. And but if you think about it, you can get those operations from these. So you're not adding anything to the group by doing those. Not immediately obvious.
So Joshua, earlier you said something about interesting. Is it going to come up again what interesting means? Why the 17s are uninteresting?
Yeah, essentially my last slide where I say almost nothing. I'll comment on that. Yeah, there's some, I could say something about it now. There's some sense in which, right, a puzzle is harder or easier. If you download an app, it'll usually give you, here are the easy ones and here are the medium ones and et cetera, right? And that ranking is sort of what I'm referring to there. But that's something that apparently is just the humans who make these puzzles are, decide how hard it is. And when they publish the puzzle in the newspaper and they write at the bottom, oh, this is a medium difficulty one, that's just a human decision. One interesting question, and like I said, it's on my last slide, is how is there any reasonably defensible mathematical way to estimate the hardness of a puzzle? I think there's a bunch of interesting questions there. And unfortunately, I don't have time to talk about it today, but there's a whole set of interesting questions. So yeah, so let me look at something that at first looks like it probably trivial, but it isn't. Sudoku, which is 4 by 4. So right, we can generalize Sudoku. Just take the same rules. You have an n squared by n squared board. Your n is 2, and again, you've got rows and columns and these blocks or boxes. And okay, well, if you wanted to do it here, right, this would be, let's try to count what's the fewest number of givens for this thing, for Sudoku. Well, okay, so you'd want to check all the possible 4 colorings and then maybe only count 1 from each equivalence class under the order 2 Sudoku group. And well, okay, this thing has 16 cells, of course, which means there are 4 to the 16, a lot of colorings of this board. Now, if you try to do just a sense of scale here, if you try to do 10,000 a second, it would take 5 days to blow through those. So even 4 by 4 is already non-trivial. But you might notice right away, you can cut this down. That's sort of ridiculous to check all these 4 to the 16 boards for anything, because, well, the colors that you put in those, the 2 by 2 in the upper left-hand block, those are, you could just rename those colors and however you like, right? So there's you could just mod out by this S4 that's acting on the colors. And well, that's size 24. So that's going to reduce the set of things we have to think about. We only have to color the other 12 cells. That's 16 million, which at the same pace would take 28 minutes. Okay, that's a little bit better. Notice also, just, sort of giving a hint as to where this is going. When you try to count these things, you're trying to get one element of each orbit, each equivalence class. And so you can use things like this. Notice if you have this board, the Sudoku board, and if you swap two of the columns or rows, of course, this preserves the property of being a valid coloring. So there's a swap of those two columns. There's a swap of those two rows. So because of that, you can assume that the yellow square that's in that lower right-hand block, that it's in the upper right corner of the lower right block. And then, multiply by 4 because there's this group of order 4 that's acting on the board here. So that's a way to reduce the complexity of the number of things you have to look at. And well, you can keep going. Of course, that gets it down to 4 to the 11, which would take you 7 minutes at that pace. And okay, well, it turns out if you keep going with this, the orbit of the Sudoku group it's actually, you only get 2 orbits. And there's a total of 288 boards. So this is a fun little exercise to convince yourself there's only 2 sort of truly distinct Sudoku boards. And then everything else you can get by just acting on it with the order 2 Sudoku board. And if you might wonder what's the connection with inequivalent puzzles. Well, of course, these groups are acting on the puzzles as well, because you're just hiding some cells. And so you can think about inequivalent puzzles in the same framework. It turns out there's like, I looked it up a few minutes ago, there's 85,000 puzzles in Sudoku and something like that, and there's exactly 4,800 inequivalent ones. That's probably not an easy exercise. All right, so well, if we're going to try to count or look inside Sudoku boards to find fair puzzles and look at what's the fewest number of clues they have, we're going to need to enumerate all the Sudoku boards. So how many are there? How many 9x9 Sudoku boards are there? And if you think about it for a minute, it's actually a little bit subtle because of the dependencies between rows, columns, and blocks. It's a little complicated. It turns out there's about 6.7 sextillion 9x9 Sudoku boards, standard Sudoku boards. This was figured out in 2005. There's a link if you want to go look for it. Of course, it's a little bit unsatisfying because that's not up to the action of the Sudoku group. So you might wonder how many truly distinct ones are there. Well, there's about 5.5 billion of them up to this equivalence. There's about 5.5 billion Sudoku boards overall. So if you download an app and you solve Sudoku all day, it's got a pool of about 5.5 billion that are interesting. Then you start to repeat yourself. So of course this is way too many to check. You could, in theory, right, like take each one and look at all their 16 clue subsets and see if any of them are fair puzzles. But this is absurd, right? It's not possible generally. Too big. So why can't I advance the slide? There we go. Just to point out, this is the generalization in the other direction, right? So Sudoku goes down to 4x4. This is going up to 16x16, where fortunately hexadecimal exactly lets us fill the cells with one symbol. This is an example of a 16x16 generalized Sudoku board that I found in the wild somewhere. And I didn't type all of these, I don't think. This, I'll tell you what this Sud sub n thing is in a bit. I didn't define that yet, but you get the idea. This is the generalization. Same rules, just that now we've got 16 symbols and they each have to occur in each row, column, and block. And you might wonder how many of these are there. So this is completely out of hand. We have no idea basically how many of these Sudoku boards there are, generalized Sudoku boards, the 16x16. We have no idea how many equivalence classes there are. So there's a big question there. How many are there? Even just asymptotically, how many Sudoku boards are there? generalized Sudoku. And by the way, like some people have tried to make some sort of reasonable estimates using some probabilistic heuristics, and I guess people believe it's like 6 times 10 to the 98 Sudoku boards. I think that's not up to equivalence, just raw 16 by 16 generalized Sudoku boards. So a lot. I'd like to know what's the growth rate of that. Would be a good thing to answer. We don't know. So I gave this talk, or some very early version of this talk, before the following paper came out, and so my story had to change. So McGuire, with a couple other folks at University College Dublin, had this paper. It came out January 1st, 2012. There's no 16 clue Sudoku, solving the Sudoku minimum number of clues problem. So the claimed result is that there are no 16 clue Sudoku puzzles. In other words, that number really was 17, that there are 17 clue puzzles. I showed you one, and there are not 16 clue puzzles. So the minimum number of clues question, the answer is 17. Well, at least that's what this paper claims. Let me talk about that a little bit. So it's been refereed, it's appeared, and it appears to be correct. I mean, I read it and I don't see any problems, and other people have read it and not seen problems. Okay, so how in the world did they do that? Because this is, these numbers we were just talking about are just outrageous, right? So a little hard to see how you would do this. And then, okay, so the strategy is they're going to reduce the problem to something, quasi reasonable, and then some very clever programming, and then throw a giant computer at it, right? So they've got access to some very serious computing power. Namely, they report in the paper that the overall computation was 7.1 million core hours on a 320 node machine, each of which had two processors with each which had 6 cores, 24 gigs of RAM. Anyway, like serious machinery, right? And it took them a year, and also took about €1 million. This is when people say like, how, if they're skeptical of funding, theoretical mathematics, this is not the example that I provide them because it is not, it's politically untenable. But I like this result. It's yeah, but there's good reasons to do this, right? That are not just the answer 17. But it's a whole other talk. So what's the strategy here? So basically we're going to take these 5.5 billion inequivalent boards. So just make a list of all of them. This was done by Glenn Fowler at AT&T Labs. It's a full enumeration. And then of course this is it's a huge database. So you got to store it in some clever way that is actually going to fit on a hard drive. So the uncompressed size, it turns out, was like 0.5 terabyte. There's some very clever compression that is like custom compression for this data that Fowler used to provide the data. It's only got it down to 6 gigs, which is pretty good. Notice that that's just 8.77 bits per board. Kind of amazing. Yeah, so then what, right? So you're going to take each of these 5.5 billion boards, and you're going to take each one and you're going to look at all possible ways of picking 16 givens from it. And then among those 16 given proposed puzzles, see if they're fair. And you just make sure they're all unfair. And then, in the end you say, no, none of them were fair, right? That's the game. Well, of course, immediately another one of these astronomical combinatorial explosion problems, which is that there's 81 choose 16 subsets of the cells that you could possibly have as your givens. And that's, it's about the number of seconds since life began on Earth. Big numbers. It's not going to be possible to just do that computation as is, but now 10 to the 16 is getting, within the ballpark of human lifespans. So, and modern computing. So we're getting there, right? That's sort of the strategy. So McGuire and folks were, okay, they were smarter about which cells to look at. That's really the key here. So what do you do? Here's the real central observation. notice that any fair puzzle in this board, so you take this board and you take a subset of the cells, any fair puzzle is going to have at least one of those red numbers, right? You see the 9s and the 5s there. Why? Because, well, you could switch the 9s and 5s and preserve it being a Sudoku board. That's a Sudoku trade. It's sometimes used in the literature about this topic. So yeah, right, you could switch it, which means you have to pin down those 4 entries by knowing at least one of them. So any fair puzzle, if it's going to be fair, it's got to have an unambiguous solution, which means you need to have those one of these 4 cells in your set, in your minimal set of givens. So let's call those 4 entries in the matrix. Let's call that an unavoidable set of cells. And then these blue ones, these 6 blue ones, it's a more complicated example of a unavoidable set. There's a kind of, you can notice there's a kind of cycle. There's a C6 there, and you could just switch the 4s and 9s and preserve it being a Sudoku board. Is a more complicated Sudoku trade. And okay, so we're gonna basically we're gonna take each completed board and we're gonna look at all of the unavoidable sets that board admits, or at least lots of unavoidable sets that board admits. And then within each one of them, given each one of these boards, we're going to try to come up with a list of all the sets of 16 cells that hit each unavoidable set at least once, right? Because that's the property that we need. You need at least one of these entries in each unavoidable set. And this is really Maguire et al.'s strategy. And then, once you have a set of 16 cells, you're just going to check each one to see if it's fair, or maybe I should say check that it's unfair. Right, and so, okay, so one of the ways to get these unavoidable sets, which it turns out is non-trivial, you can, Ed Russell came up with this list of 525 blueprints, which is actually all of the potential unavoidable sets on 11 or fewer cells, and then some larger ones as well. And then you can apply the Sudoku group to that action, or that set of actions, to the blueprints, and then you get a whole bunch of different unavoidable sets that way, right? And then you can just compare it to your puzzle and make sure that your puzzle actually hits each one of those unavoidable sets at least once. So here's just an example blueprint, and you can imagine, acting on that with the Sudoku group, and it's going to move around the board, and you just, for each one of those unavoidable sets, you have to hit at least one of the entries in the unavoidable set. So, okay, we're going to enumerate all the sets of 16 cells that hit each unavoidable set at least once. Unfortunately, that's hard. That's the hitting set problem, or a special case, but not terribly special case of the hitting set problem. That's well known to be NP hard. So well, it's not as bad as enumerating all the 18 or 81 choose 16 sets of cells. So, there's an improvement over the completely brute force approach here. These hitting sets that have at least one element in each unavoidable set, they're also known as transversals to the collection of sets, to that set system. It's just a transversal, given a set system, is a set which intersects each of the subsets in your set family.
And
right, so the algorithm now, yeah.
Just to make sure that these unavoidable sets are based on the actual solution, the full set, they're not geometry in the abstract, right? Yeah,
that's right. So the which unavoidable sets can occur is going to vary from board to board, because you can imagine, one way to construct one would be pick a number, pick another arbitrary number in its row, then find the first number in the column of the second number you picked, and then see if the fourth number in the rectangle is the same as the second number that you picked.
Okay.
So yeah, you have to do searches like that. Yeah.
And so I think that was Hayes' question. How long does it actually take to find these unavoidable sets? So this is how hard it is to check the transversals. Is it also hard to check the other? Do you know?
I'm not sure. I mean, whatever it is, it made the computation possible. But yeah, I don't know. I haven't tried to do that myself. Yeah, it's certainly. So they're not trying to find all of the unavoidable sets, I should say. So that's probably a lot harder, right? But or rather a set of, many unavoidable sets, so that, the idea is the more unavoidable sets you get, the fewer of these transversals there are. And so that whittles down the set of things you have to check to see if they're unfair. But you don't have to find all the unavoidable sets. You might end up with something that's not transverse to the set of all unavoidable sets, but is for the ones that you've found thus far. And okay, so actually another little improvement, it turns out this is really enabling of the computation. Once you know that you hit a set, you don't have to check whether it hits the other one. So you have these sort of dead cells in each unavoidable set. So you don't have to add the clues or add potential clues from those unavoidable sets because well, you already hit that set, right, is the idea. Now, you got to be careful because they may be in other unavoidable sets. Usually they will be. So there's some serious bookkeeping that's needed here. But it turns out like doing that right is a key step also in their being able to complete this this computation. Okay, one little issue that is probably, is this thing a proof? This computation, this year-long thing of proof. So part of the problem, of course, if you heard the saga of the the Kepler conjecture or the earlier four-color theorem, right? There's this famous question: is this thing a proof? Part of the problem, of course, is that the computation itself is way too big for a human to check it. I mean, it took a very fast, heavy-duty computer a year to do it. Human can't. And well, okay, so as long as our understanding of physics is sufficiently accurate, that we have a complete description of the behavior of the processor given an instruction set, then you should believe the computation, yes. Well, unless there's a bug in the code, and everybody knows it's basically impossible to have bugless code. Or, ooh, this one's even worse, right? So what if there's a bug in the OS or the firmware that's running the code? Like, there's a chip in the bus that's just communicating between the processors. Are you sure that its firmware is correct? Probably not, right? But you actually can't even look at it because it's proprietary and it's covered by intellectual property laws, and so that's a problem. That, I mean, is probably not really a proof. And then well, this one, this one's annoying. What about cosmic rays streaming in from outer space and striking an atom high up in the atmosphere and then causing a a cascade of muons that hit a gate and flip the charge state of a gate in your processor and flip a bit or something? Well, that's sounds bad, right? But also, actually, you could have your walls are usually made out of some kind of rock, and that was mined, and that's not radioisotopically pure. So there are radioactive atoms in there, and they're going to toss off alpha particles, or generally alpha particles are the problem here. And that could strike a transistor and flip its state. It's not just coming from outer space. Also, there's like random noise coming from crosstalk, capacitive crosstalk, inductive crosstalk, that can cause, because the features on modern chips are like, 15 nanometers or whatever. It's only a couple hundred atoms wide. So this is you can totally get quantum effects that get bad, right? You can get bit flips. That's a lot to worry about, right? So the question is, how real is this? Are these really things you got to worry about? I mean, you might wonder, maybe these are all just hand wringing over nothing. It's just for philosophical issues. I actually think the philosophical issues are interesting and serious, but even just the physical issues, do we have to worry about the output being wrong? And it turns out, yes, it's actually kind of bad, the situation. And so, for example, like NASA knows this, and they harden their chips. You don't want your life support systems to malfunction. So they harden all those chips that go up into space, have error correcting memory and shielding, and because this is actually well known already. This found a paper. If you go looking for this thing, you'll find tons of examples of people talking about observed bit flips. So this semiconductor company does this white paper from 2004 where they observed somewhere between 1,000 and 5,000 bit flips per billion hours of use per megabit of memory. That actually adds up pretty quickly. There's a more recent result, 2009, by some folks at, I think it's Texas, UT, and also Google. This DRAM errors in the wild where this is a very disturbing sentence. We observed DRAM error rates that are orders of magnitude higher than previously reported, with 25,000 to 70,000 errors per billion device hours per megabit, and more than 8% of DIMMs are affected by errors per year. We provide strong evidence that memory errors are dominated by hard errors rather than soft errors, which previous work suspects to be the dominant error mode. This is really concerning. Soft errors are when a bit flip happens, and then when you go back to repeat the computation, it doesn't keep occurring. A hard error is when there's like damage to the hardware and it keeps happening. So they actually saw that hard errors were the dominant source of problems, which is that's really concerning, right? And for example, like another thing, if you just go searching, you can find this blog article where Neil Gafter documents. It's actually remarkable how he hunts down. He found a bit flip in his RAM, in the copy of the Ubuntu Linux kernel sitting in RAM on his machine. Found a bit flip in the EXPR, which is some helper for evaluating mathematical expressions, part of the kernel. Found a bit flip that actually caused seg faults. So this is very real, right? Actually, Toyota's the stuck pedal incident, where they lost the lawsuit, the 2013 lawsuit. This expert on processors, and particularly the kinds of errors that can occur, I just ripped it from Wikipedia, testified that a single bit flip is one of the potential causes of that stuck pedal issue, was that a single bit flip can cause unintended acceleration due to cosmic rays. So these can even kill you. This is a real serious issues, right? It's not even theoretical. So that million euro year-long massively parallel computation probably had lots of errors in it. Now, did it affect the output? Probably not, but that's not a proof, right? It's good evidence, but it's not a proof. So what do you do about this? Of course, that's the natural question. How do we still want to be able to use computers to help us do our math, but is there any solution to these terrible problems? Well, yeah, the standard answer to this these days is we come to a détente on the issue, which is output a certificate. So, basically, somewhere publish a proof, even if it's not human readable, even if it's just the trace of your computation that led to the output. Right? If you tracked all of the computation as it occurred, well, you could publish that trace, and then somebody could check that there were no errors. Of course, they'd have to check it using another computer, which itself could be making an error, but this at least keeps your proof in the realm of checkability. That's the idea. This one reason you might object to the, often if I talk to somebody about this issue of are computer proofs, they go, well, humans make mistakes all the time. There's so many examples of proofs that have fallen apart after some amount of time. The four-color theorem is this very famous example of this, with Tate and Kemp's proofs. And so, computers are way more reliable. Shouldn't we count the computer proofs as reliable, as more reliable than human proofs? Humans make mistakes. It's true, but human readable proofs continue to be examined, right, for the rest of eternity. And so, one hopes. And so, as long as you keep your proof in the realm of checkability, even if it's just computer check, at least the probability that there's an error tends to zero with time. It doesn't just, end up being 10 to the minus 20 and then it's fixed there forever. You hope that people keep re-examining it. So if you're wondering, what does a certificate look like? Here's an example I just pulled from GitHub. This is what the Coq system, the proof system. I guess somebody named Carl Palmskog published. This is a proof of the Pythagorean theorem in that system. It's actually pretty readable, but longer than your average proof of the Pythagorean theorem. But if you look on the bottom left, there's a bolded theorem. That's the output. But you see the rest of this. There's these like lemmas and definitions and things like that. That's sort of what these tend to look like. Is a very standard way to do it in French, at least. You might have noticed it's in French. So okay, that's the answer is output a certificate. Well, okay, that's also got problems. One is not everybody knows how to do that or has the time for it, frankly. The proof itself is pretty unenlightening, right? Like this thing I tell my students, proofs essentially serve two big purposes. One is to certify that the thing is true, and the other is to explain what in the world is going on. Those are both very useful things that proofs give us. And well, that proof that you just saw was not, it doesn't serve the second purpose very well, that explains what's going on. So, okay, it isn't great in that respect. And then, okay, it's also, it's way easier, as McGuire found, right, to run a calculation than it is to run the calculation and output a proof that the calculation is correct. You have to have a whole other layer of computation going on to certify that your answer is correct. It turns out there are systems actually that will always output a proof. You have to actively throw away the proof of your computations, but they're slow. They're not nearly as mature as all of the computational tools that we have access to. So, hard to instantiate your favorite calculation this way, unless it happens to be one of the things that these systems do well. Also, of course, there's this problem of bit rot. You store I have a proof, and then you store it on a hard drive somewhere, and then you come back to it 20 years later, and you can't read the hard drive because some bits evaporated because they got struck by cosmic rays, or they're just some random quantum effects, or things can happen. Also, hardware obsolescence is a serious problem. For example, I guess there's a whole lot of software from the very early days of AI research that is now unreadable and unusable because there's no machines to run it. The software that was written to run it was like custom builds of software that's now standardized, but wasn't at the time. And so we literally have no way to run these things. And then there's also the issue of dependency hell. So this is, if you need to know which libraries even need to be called in order to process the, for example, that certificate I showed you before, to check, is it correct? And, these depend on things, which depend on things, which depend on things. And you can easily break that chain. People try to, archivists try to refactor code in order to keep it current so you can continue running it, but you can very quickly break dependencies this way. So, yeah, there's all kinds of problems. I mean, it is a kind of solution to this, but it's only one kind of solution to output a certificate. And then, okay, well, here's another solution. Let's just do math, right? Let's think about this some more and just hope that we can come up with a human readable proof. This is obviously a objective that mathematicians of the world would like to see. For example, to my knowledge, we still don't have a human readable proof of the four-color theorem. So, even though we've got a number of formal proofs of this thing, none of them are readable by a human. Still waiting on that proof that explains what in the world is going on. So okay, so let's talk about what's the framework for thinking about these things mathematically. You want to answer this question, the fewest number of given. So let's define a graph, Sud sub 3, on the set of cells. So this has got 81 vertices, and it's this thing. So I've replaced subscripts that normally would be numbers with a set. That's the vertex set. These are complete graphs. That box denotes Cartesian product of graphs, and Cartesian product is associative, so you can just write an exponent. That's this graph. Well, actually, I'm showing you only the second, not a sum and union and whatever the second part is. That's this graph that I've got pictured here. So you've noticed what we're doing here is we're making it so that the graph, its colorings are the same thing as as Sudoku boards. These are the edges are just the prohibited pairs of colors, and so you get prohibition of repeated colors within each of the blocks, and that's these 9 K9s, and then In the rows, you get 9 K9s, and then the column you get 9 K9s, right? So the union of all of these is this horrible thing that I broke up into those 3 pieces because this is horrible. So that's the graph, that's the Sudoku graph, and really we're just studying colorings of that graph, right? That's ultimately what all of these Sudoku questions are about, is colorings of this graph. But just so we're all on the same page, what I mean by coloring, right? So that I'm talking about proper colorings. So the chromatic number of this, the Peterson graph, means, you know, the fewest number of colors, so that it's the smallest k, so that it's k colorable, right? Where what I mean is we're going to assign k colors to the vertices, the most standard kind of coloring. Assign k colors to the vertices in such a way that no edge has both of its end vertices getting the same color. And the chromatic number, right, is the smallest integer, so that it is in fact k colorable. So this graph can be colored with 3 but not 2, so its chromatic number is 3. So right, so if you have a graph G and you've got a proper vertex coloring, that's sometimes it's called an optimal coloring if you're coloring it with the fewest possible number of colors, namely chi of G. Then a determining set, that's a set of vertices, so that the coloring restricted to those vertices can be completed to a proper vertex coloring of the graph in exactly one way. Right, this is, you can imagine, this is the set which will induce a fair puzzle, and for a given coloring. And so, you know, just to succinctly say it, it's a determining set, is a set of vertices that determines the rest of the coloring in any graph. It doesn't have to be that Sudoku graph. A critical set is a minimal determining set. So, you know, the interesting thing here is, you know, you don't need to study the 17 clue sets if they all have a vertex that can be removed and have it still be determining. Right, you need the minimal ones to find out what's the fewest number of clues. So those are called critical sets. The minimal determining sets, of course, for example, all of the vertices, the entire vertex set, that's a critical set, or that's a determining set, but not a critical set in general. So yeah, let's just have some terminology. SCS, the size of the smallest critical set, SCS. Given, so this takes as input a graph and a coloring, right, an optimal coloring. It's just the size of the smallest critical set for that graph and that coloring. And then LCS, the size of the largest critical set, given that graph and the coloring. The minimal critical sets can range in size, which, because I didn't say minimum critical set, I said minimal, right? You just can't remove any points. They're not necessarily the smallest. So the interesting question, you know, what's the smallest, what's the largest, given a graph and a coloring? And then those quantities you can maximize and minimize over all the colorings of a graph. And these are just, so you get 4 parameters for a graph, right? The size of the smallest critical set over all colorings, and then the size of the largest size of the smallest critical set over all coloring, et cetera, right? So you get 4 parameters this way by maximizing, minimizing over all the colorings. And yeah, so the claim, right, this theorem is that it's 17. And okay, right, so we're going to try to study this quantity by, well, maybe study the growth rate of this thing. Well, with Anna Kirkpatrick, who's now at Georgia Tech, we showed that for a even cycle, they're all 1. You should convince yourself of that. It's actually not hard at all. And then for odd cycles, it actually gets way more interesting. We pinned down the numbers for all the odd cycles. And you might notice they're ordered this way. Those are greater thans or greater than or equal to's. There's a poset here, small one. Right, they're naturally ordered in a simple way. And it turns out all 4 of these parameters, unfortunately, are NP hard to compute. Actually, they're probably, is it pi 2 or sigma 2 hard to compute? They're probably the next level up too. But we only show they're NP hard. To say what I mean is that to certify that they're greater than some given number is hard. So by the way, a lot of this language is coming actually from Latin square theory. Latin square of order n it's Sudoku, but without the blocks. So you have an n by n matrix. Here's a 7 by 7 Sudoku board where you fill with the numbers 1 through n, and you know each row and column has to have the numbers exactly once. So the Latin square graph is just the Cartesian product of 2 complete graphs. That's the thing whose colorings are the Latin squares. That's you can ask, you know, what is its smallest chromatic, or what's the smallest critical set for that graph? This is actually from 2007. That was the first superlinear lower bound. It's already pretty hard to get superlinear. Even getting a large linear constant times n is hard. And then Hatami and Tian in 18 and just a couple years ago showed actually they got a quadratic lower bound, which, you know, the upper bound, of course, is n squared, trivial upper bound. So that's kind of best possible, although the conjecture is that it's actually n squared over 4. Is if interesting code, but they got n squared over 10,000. Probably a little bit better if you're careful with the numbers. But it is kind of amazing that they were able to do that after all the work that went into showing that it was super linear. And then other folks have shown that it's okay. It's certainly at most n squared over 4 floor of that. Here's just a smattering. I realize I'm running out of time. So smattering of some other results on this topic. People have analyzed these. They usually don't refer to it in this language, the SCS and LCS, but you can cast it all in this language. We showed with Anna similar result to this Kandahari Hatami Mahmudian result. The smallest critical set is upper bounded by something that at least is smaller than n squared by n to the 5/3, where capital N is the size of the board, right? Little n squared. And notice something that comes into play here is the notion of unique colorability. So a graph is uniquely colorable if it's only got one coloring, up to permutation of the colors, of course. All these numbers, if you think about it for a minute, they're all just chi -1 if it's uniquely colorable, because I just have to tell you for each color class, I just have to tell you one vertex from that color class what its color is. And then, well, except for actually one of the colors I could leave out because you can figure it out from the other ones. It's the leftover color. And so it's just chi of g -1. In general, the smallest critical set is always going to be at least chi of g -1. And you only get equality when g is uniquely colorable. Actually, this is a really neat exercise. This is surprisingly hard to show that the smallest critical set of a graph, the size of that, is chi -1 if and only if the graph is uniquely colorable. This is a really neat little paper. It's only about a page long, the proof, but definitely not obvious. By the way, like this unique colorability, which makes, you know, all of these questions sort of boring, right? This theorem up there. It's more common than you might think. So you got to search a little bit for the interesting questions about these 4 parameters. All of these graph classes are uniquely colorable. So it's kind of boring, these examples. But of course, there's things like the Sudoku graph that are interesting. The set of colorings there, those are not uniquely colorable. There's lots of Sudoku boards. And then also let me just mention this, maybe my favorite problem here. What's the list chromatic number of Sud 3? So list chromatic number is the smallest k, so that if you put a list of k colors at each vertex, it's always possible to pick a color from each of the lists so that you get a proper coloring. So here the idea is that the colors on each vertex are not necessarily the same pool of colors. You have k colors, in the classical coloring question, you've got k colors, but they're all the same at each vertex. Here we're allowing k colors, but of your choice, your choice at each vertex. There's a list sitting at each vertex, and you're going to pick one. So, you know, here's a Sudoku board where in the classical case, you've got the numbers 1 through 9. You're going to pick one number from each cell to make it a Sudoku board. And so here's an example of painstakingly circled an actual Sudoku board. Right, that's a list coloring from those lists. But what about if the lists are just some symbols? Like if I just populated them with like random sets of 9 symbols, can you always find a board from these symbols that is an assignment from these lists that it obeys the rules of Sudoku? I don't know, actually. If you have 9, maybe it's 10, maybe you need 11. It's unclear. It's a nice question we know absolutely nothing about. And you know, of course, this you may know of the Dinitz conjecture and Galvin's proof of it. The list chromatic number of the Latin square actually is n. So somehow the blocks or the boxes here, the 3x3s are the hard part. And actually, we already don't know the answer to this question for the Sudoku for 4x4. It should be doable with a finite computation, but I haven't been able to do it. I'd be interested if anybody knew it, how to go about it. So yeah, just to leave you with a couple open problems. Of course, maybe my favorite question is that what's this list chromatic number? We know essentially nothing about this. Of course, the question I asked early on, which is how many n squared by n squared Sudoku puzzles are there approximately, or boards for that matter? How many are there asymptotically? What's the growth rate of that function? What's the fewest number of clues in an n squared by n squared? You know, of course, you could ask that question about the generalized Sudoku board, and we know virtually nothing about that. This I didn't have time to talk about. There's a whole other talk one could give on this. How do you pick them at random? Of course, you could just reach into the bucket of 5.5 billion Sudoku boards and pull one out uniformly at random, but that's not how it's done generally. So can you generate one uniformly at random, at least asymptotically? So is there a Markov chain, for example, that you could sample from to generate these things? There's a lot that's not known there, basically everything. And then also, as I mentioned earlier, how do you measure the hardness? Is there any defensible way to measure the hardness of Sudoku puzzle output? So this is a hard one. This is an easy one. I actually have a little bit of work with a student where we tried to evaluate essentially the depth of the logical tree you'd have to traverse to the decision tree to figure out how what you could put in a cell and use that as a gauge. It was a very rough gauge though of the hardness of the puzzle, and didn't seem to capture the intuition very well. So with that, I will thank you very much.
All right, if everybody wants to unmute and clap for Josh, say thanks. And if anyone has any questions they'd like to pop into the chat or unmute themselves and ask, please feel free.
That depth of the tree idea, I heard something a while back that, so like when I do them, I sort of deduce the ones, and then sometimes I get to a situation where I have to say proof by contradiction, where like, let's suppose this is here, and then I find out, and then I retrace. And I heard that like one measure of the difficulty was whether or not those brute force strategies had to use that hypothetical one, or how many times it used it. Is that sort of the same thing as the depth of your? Yeah, that might be the same. Yeah, right. Like, is it one way to? Yeah, you could trial things, right? Like pencil in a number and see if it breaks the rules eventually by looking at the consequences. Yeah, the how many guesses you have to make is kind of the idea, right? Like how deep you have to go. Okay.
So I probably, as similar to many people, wrote a Sudoku generating program and tried to make a classifier to classify them according to, I tried to program in human strategies and classify them according to what strategies were needed to solve it. So I don't know, has anyone done any work along those lines?
So I've seen nothing published on this topic. Yeah, there seems to be no work on the question of how hard, or how to measure the hardness.
So I mean, I have I picked out, I think I got 3 strategies that distinct strategies that I use, that I observed that I use when I solve a Sudoku problem. The lowest one being the kind of forced square. There can only be this number in this particular thing. So I kind of said it's an easy one if you can fill it in only using forced squares. And then I picked a couple of other strategies, and generally I find that with randomly generated Sudokus, it can generally be solved either by forced square or with 1 or 2 other rules that I have. And I use sort of how many of those do you have to use in order to classify it between the various different levels that you can say, and that if you have to go to essentially a guess, then that's like the top level of classification in my system.
Yeah, there's certainly. So I think, I mean, my impression is that some of these apps that will generate a board for you to solve, generate a puzzle to solve, are at least they make maybe this distinction between the easy and the ones that are above easy, harder than easy. That distinction seems to be whether you ever have to guess.
Right. So I mean, I guess I've got a couple of levels between the sort of guessing and the 4 squares. But anyway, I don't want to. I'm sure other people have questions, but I don't know if anyone's interested in talking about that, I'd love to discuss with anyone.
Kate,
So somebody asked in the.
Go ahead.
Sure. I was going to bring up the question from the chat. There was something I was wondering about too, about the relationship between the number of givens and the difficulty ranking of the puzzle. I mean, is it always true that the easy puzzles have more given information at the start, or is it not necessarily connected in that way?
Yeah, so from what I hear, the hardest puzzles tend to be in the low 20s in the number of givens. There seems to be, it's like unimodal. It's easy if you've got too many, but then also this, if you only have 17 clues, right? It's so constraining in what you can put down that they end up being easier to solve than your average 20 clue puzzle. Sort of unexpected phenomenon. But yeah, I think my impression is it goes up and then back down again and peaks in the low 20s.
It's really interesting. Now I want to go back and count how many givens were in some of the puzzles I've solved lately.
Yeah.
All right, well, we'll wrap up our recording now. Here we have on our screen our next couple of talks. So next week, Samuel Hansen will be talking to us about, can you tell me a story? This is going to be a really great talk. If you don't know Samuel, they run the podcast, the Relatively Prime podcast, so you can go and track that down. I think that it'll be a really fascinating talk. And we're hoping to get more listed up on our calendar for October. We're currently booking a couple of people. So stay tuned for updates about that. And we're always looking for abstract submissions. So if you know anyone, if you're interested in submitting an abstract for an entry-level engaging talk like the great one that Josh just gave, you can definitely do that on the Talk Math with Your Friends website, and we would love to see it. So why don't we all thank Josh again, and then we can stick around and chat. So thank you, Josh. This was awesome.
You're welcome. Thank you for the invitation.